Hi guys and welcome back to the ACE Academy. In this video, we'll be looking at electromagnetic radiation. The first question that we are going to ask ourselves is, of course, going to be, what is electromagnetic radiation? In a nutshell, electromagnetic radiation is simply light, which means that in this section, we are mainly going to be investigating what light is, its properties, and how to use it in our calculations. Now, from our understanding, light is a form of energy. Now, the energy that light emits, or the energy that light is made up of, can have two types of properties, or rather, it can be classified as two different types of energies. But in fact, it is the exact same thing. Now, that is a bit confusing at first, but we are going to explain it and get into how light can be two things at the same time. So, because of light's special ability to exhibit the properties of two different types of physical quantities, we say that light has a dual nature. Now, to understand and explain why light has a dual nature, we are going to investigate the two types of natures that light has. The first nature that light has is what we call a particle nature. Now, this nature is due to the fact that light transfers energy in a way that mimics matter. That means that the energy that light transfers is able to exhibit some properties of matter. So, just as an example, I have a picture of a flower pot. Now, for example, I have a flower pot in a room. In this room, I also have some sort of light source. And of course, I as the observer will be in this room. Let's have a look at how energy is transferred in order for me to see the flower in the room. So my light source emits some sort of energy that is directed to the object that I'm looking at. This object will then absorb certain frequencies of light and reflect the rest. Those light frequencies that are not absorbed by the object are then reflected back into my eye, where it is then translated into visual information that will allow me to see the object. This entire process is a transfer of energy, where light bounces off the object itself and my eyes detect the light that has bounced off. This is a simple explanation as to how light exhibits a particle nature. But hey, light doesn't have mass. And we know that any sort of matter, any type of matter, will always have some sort of mass. But hey, the transfer of energy without transferring matter is a property that waves exhibit. And that's where we get the wave nature of light. The wave nature of light unlocks entirely new possibilities for us to observe and understand the properties that light possesses. Waves have certain properties like amplitude and frequency as well as speed. So that means that light must have an amplitude, frequency, and speed. Due to the variance in properties like amplitude and frequency, we are able to analyze an electromagnetic spectrum, which explains how the type of light correlates to the properties that the light wave has. Let's have a look at the electromagnetic spectrum together. When we think about the colors that we see in our daily lives, we think about these colors right here. But it turns out these colors actually are a small part of the electromagnetic spectrum. They only fall under visible light, the light that we are able to see. This type of light wave has a moderate frequency and a moderate wavelength. As we move on to the right of the visible light spectrum, we can see that the wavelength becomes shorter and shorter. We move on to ultraviolet light, then X-rays, and then gamma rays, which are the shortest wavelengths in any form of light. Moving to the left of visible light, we move on to infrared, that is a longer wavelength. We then move on to microwaves, which are an even longer wavelength, and we move on to radio waves. Despite these waves having different wavelengths and different frequencies. One thing will always remain constant when working with light, and that is the fact that the speed of light is always constant, and it's denoted by the letter c, and the speed of light is simply 3 times 10 to the power 8 meters per second. Now that we know that light has a speed and that the speed of light is constant, let's go ahead and work with some wave properties in order to investigate how we can use this to work with the properties of frequency and wavelength for any type of light wave. We know that wave speed is equal to the frequency of the wave times the wavelength. That comes from your basic knowledge of waves. If we investigate this equation further, we can replace the speed of the wave by the speed of light. Because light travels at a constant speed, it'll always be the same value. We would get c is equal to frequency times lambda. Manipulating this equation, we would be able to calculate the frequency of any type of light wave using the wavelength, if that is given, or we can calculate the wavelength of any type of light wave using the frequency. And that simply stems from our ability to manipulate the equation. We can manipulate the equation as such. We can make frequency the subject of the formula, where frequency is equal to the speed of light divided by the wavelength of the wave we are working with. We can also make wavelength the subject of the formula, and we will obtain lambda is equal to the speed of light divided by the frequency of the wave that we are working with. But hey, we are working with the transfer of energy. So moving back to the particle nature of light, we denote light's ability to act as a particle by introducing a new type of particle, and that's a particle that we call a photon. A photon is simply a packet of energy. Now that we know that a photon has the ability to transfer energy, it's a packet of energy, we need to try to work out how much energy each individual photon has. We are now going to use the energy equation for a photon, and that is simply the energy of a photon is equal to the frequency of a photon, the number of times or the number of photons that are present in 1 second, times a constant value which is known as Planck's constant. We can further manipulate this equation by saying, hey, if frequency is involved in this equation, we can substitute frequency for the speed of light divided by wavelength, and we'd obtain the equation energy of a photon is equal to Planck's constant times the speed of light divided by wavelength. And using our algebraic skills, we can clearly see that the energy of a photon is equal to Planck's constant times the speed of light, all divided by the wavelength. So we can interchange the values given to us by working between the wave nature of light and the particle nature of light. That's it for me, guys. All the best, and I will see you in the next one.